Okay, physics, here we start section 3, complex resistor combinations. When they say complex, basically they mean more than one resistor, probably something in parallel. It's still, by circuit standards, very, very simple. It's going to be a little more complex for us because we haven't done it before, but there are far more complex things about circuits. So we're just scratching the surface here with this section. So a couple of things about circuits and so forth. One is we do have to have a circle for the electricity. We also want to be careful not to have too much electricity going. So when you put things in parallel, it allows more and more electricity to come, which can overheat the wires that are bringing the electricity to the plug, and that can cause them to melt. Dangerous because it starts a fire and can burn your building down. So we put in there either a fuse or a circuit breaker. The picture at the beginning of this video was a picture of a breaker panel. Now, back in the olden days, we didn't have mechanical breakers, and so they had usually a glass tube that you could see inside a piece of a metal that would go across in between the glass, and electricity went through it. If a little bit too much went through, that metal would get hot, melt, and disconnect, and it would interrupt the circuit. Most cars have fuses in them, and sometimes small appliances and so forth will have fuses. But houses and bigger things like that, most things now have breakers so that when it gets set, all you have to do is flip the switch back. And circuit breakers trip when it's too high. Now, if your circuit breaker in your house trips, be sure you find out why it tripped, because if you just set it back again, it could go right back to the reason why it tripped. Too much electricity could go, and if the breaker doesn't trip back, it will possibly start a fire. Very popular thing in the girls' dorm to have too many things going, curling iron, hair dryer, iron, whatever, and trip a circuit breaker. I know the boys are able to trip them as well. Too many things on one circuit. So there's a lot we could say about that. It gets much more complex, but that's the basics. So the circuit breaker or the fuse must be wired in series with the rest of everything else. All right, so it jumps right into an example, and that's where we're going to go. They start with this example here, and they ask to determine the equivalent resistance. So we're just going to find out the battery cannot see that there's a 3 ohm resistor and a 6, and then in parallel and series and so forth. It doesn't really have eyes to see that. It just feels like that's one giant resistor. So if we were to simplify this down to one resistor, what would be the resistance of the whole circuit? So I've taken a piece of paper here, and I've redrawn this circuit over here. Now, it looks a little bit different because I took these resistors and I straightened them out. And as you're doing circuits and you're getting used to them, you might redraw them so that it makes more sense to you. So I took this resistor and I straightened him out and put him out this way. So this is our first setup. Now, when we go to simplifying, it's kind of like PEMDAS. You know, you do exponents first or division first, adding, subtracting, and so forth. Well, with resistors, we're going to, almost like this, parentheses, we're going to have to do this part first. So we're going to take these two resistors and we're going to add them together because they're in series. So 6 ohms plus 2 ohms is going to make 8 ohms. And then we're going to keep this 4 ohms right there. The 1 ohm stays, and the 3 and the 6 ohms becomes 3 plus 6 is 9 ohms. So these guys come down here, these two become this one, and this guy stays right there. All right, next we've got to do the parallel. And so in parallel we have to say, well, 1 over RT equals 1 over 8 plus 1 over 4. And mathematically there's two ways we could do this. We could turn this into a decimal, and for many that's going to be the easiest way. Otherwise you can leave it as a fraction And sometimes that's easier because 1 over 4 is the same as saying, 1 over 8 plus 2 over 8. So that equals 3/8. So you could say you have 1 over RT equals 3 over 8. Cross multiply, 3RT equals 8. R total will equal 8 divided by 3, which turns out 2.7. So this is going to be 2.7 ohms. Now, another way that this math could have been done, let's just do that real quick. We could say 1 over RT equals 1/8. So you can take your calculator and go 1 divided by 8 or 1/8 and find out what that is. Well, that's 0.125. And then 1/4 is 0.25. 0.25 plus 0.125, and you get 1 over RT equals 0.375. And this step here is where usually most people get into trouble, because they want to say that RT is 0.375, but no, algebraically you got to switch these two. So we find the inverse. So you're going to take 1 divided by the answer, and you get RT equals 2.666, which is 2.27. I'm sorry, 2.7, okay? 2.7 ohms, and that's the value we have for right here. Now the rest is really pretty easy. We're just going to take these 3 resistors, since they're all in series. This guy came here, this guy came here, these 2 guys formed that one. We're going to just take these 3 and we're going to add them all up. So 9 plus 1 is 10, plus 2, we get 12.7 ohms. And that's how we do an example, breaking it down into its pieces. In the next step, we're going to take an example, and it's going to ask us, well, what's the voltage across these different resistors? And so we're going to break this down and say, okay, well, this is our R. We know what our V is, and it's really going to be fun with a puzzle. It's really a puzzle. So let's tackle this big example problem. It says determine the current and potential difference across the 1 ohm resistor. That's this guy right here. We want to know how many volts and how much current is going through here, which means we're going to have to kind of tear it apart, this whole circuit. Our first goal will be to find out, we know the voltage, so we're going to have to figure out the resistance to see how much current, how much electricity is able to go through. So what's our equation that we get to always use? We're just going to use this over and over again. V equals IR. I didn't even write the voltage here in the redrawn example because we know what it is. We're going to work on getting the resistance down. So if I know the voltage and I know the resistance, I can calculate the current in the single wire part. I won't know what the current is here, but I'll know the total. But I'll have to figure out which one is which. So let's go do what we did in the last example, and let's start to break it down. So these 2 guys, they can come down. If they're in series, we just add them. So that's going to be 8 ohms. These 2 guys are in series, so let's add them together, and that'll become 4 ohms. We keep the 2 ohms here, and we keep the 2 here. All right, now we're going to leave these 2 guys alone, and we're going to put these 2 together in series. Now what's the math on that? Remember, since they're in parallel, we've got to go 1 over RT equals 1 over 4 plus 1 over 2. In this case, since the math is really easy, it's a little easier to go 1 over RT equals 1 over 4 plus 2 over 4, or 3/4. So you know if you cross multiply, you get 4 equals 3R, or R total equals 4/3, or 1.33 ohms. So this here becomes 1.33 ohms, and I probably could just go 1.3. So what is the total resistance of the whole circuit going to be? We're going to take these three guys, add them up because they're in series. 8 plus 2 is 10, 11.3 ohms. That's our total resistance. Now, my next goal is to find out how much electricity is going through this circuit. That's how much is going to go through here, and then split the two different directions. So I'm going to use that basic equation, V equals IR. My voltage I know is 9, and my resistance is so I'm going to rearrange this and divide by R. And we're going to get V over R equals I. So that voltage will be 9 divided by R, which is 11.3, and that'll give the current. All right, so let's do that. Nine divided by 11.3, and we get 0.8 amps. Well, that's quite a few amps. Amps are a pretty big unit, so this is a good current. Now, that is telling us that that's how much current is going through this whole circuit. So now we know the voltage, we know the resistance, and we know the current. But they wanted us to find out what is the voltage drop across here and the current across here. So that gets a little more tricky. So in order to figure this out, I need to figure out the voltage drop across each of these parts. So the next step I need to know is I need to know how much the voltage drops from here to here. That's what I need to figure out, from here to here. If I know the voltage drop, then I can calculate how much current goes through here. And once I know how much current goes through here, I go backwards and find out how much the voltage drop is across here. If these resistors were equal, I could just divide the voltage drop in half, but they're not. So what we do is we're going to go down and we're going to sneak down here and we say, well, what is the total resistance of that part of the circuit? So if I know my voltage equals the total resistance, which is 1.33 ohms. So I'm going to go resistance times the current. What's the current that goes through here? Well, that's what we figured out right here. So we're going to go 0.8 amps. So let's just do that on the calculator. 1.33 times 0.8. That equals, voltage is 1.064 volts, or basically 1 volt. All right, so now we know the voltage drop from here to here is 1 volt. So that means it drops 1 volt here and it drops 1 volt here. So now I know the voltage drop across here. So if I know the voltage drop across here and I know the resistance, I can find out what the current is that goes through this side. Now, since you see it's a 2 to 4, so 2/3 of the current should go through this one and 1/3 should go through this one. Let's see if that turns out to be about true. So we're going to just do with a resistance of 4. So I'm going to do another color to show what we're doing here. We're going to use the same equation, V equals IR. This time our voltage we know is 1 volt. 1 volt will equal, what's our resistance? It's 4. So our I times 4 ohms. How do I get I by itself? Well, I divide by 4, and we get the current equals 1/4 or 0.25 amps. Now that I know the current that's going through here, I know it's 0.25 amps. I know the current, I know the resistance. Now I can find the voltage that drops just across this resistor. So one more time, let's got a calculation. We're going to do V equals IR again. Our voltage is, oh, we don't know the voltage. Our current is 0.25 amps. So voltage equals 0.25 amps. Our resistance is 1. Okay, you can see the math's going to really be tough on this one. So what is our voltage drop? Well, what's 1 times 0.25? Why, our volts are going to drop by 0.25 volts. And that is our final answer for the voltage drop across that little red resistor right there. So you can see how we have to take the circuit and break it down into pieces. So that's how you're going to do the assignment on the next page. And so here's the page. Here are the answers for that question on page 652. There is no number for this question, so I didn't put a number 1 or anything like that in the assignment. And then here are the answers for this page right here. And I should have given it earlier, but here are the answers for page 649. 649 right there. Okay? All right, go for it. Keep up the good work.